Okay, good morning. So, let us get started. Over the last few classes, we were discussing some basic concepts in real time communication, then we reviewed our knowledge in communication, computer communication. Now, let us look at how real time communication can occur in a LAN environment, and we will see that there is no standard protocol that has yet emerged, but there are many competing protocols which are being used in different situations. So, let us first finish what we were discussing last time, a small part left out, and then we will proceed towards discussing about real time communication in a LAN environment. So, last time we were discussing about the internetworking devices. We discussed various types of devices that are used in internetworking: hubs, bridges, switches, routers, etc. But one thing we did not mention is that when we have an interconnection network where we have the option of using switches and hubs, where to use which one? We did not discuss about this issue. Let us just complete this issue, then we look at the real time communication in a LAN environment. If you look at any network nowadays, you will see that there are many switches and hubs in the LAN, and we know that switches cost more than hubs. We were saying that hubs are very inexpensive, can buy in couple of ₹100. Switches are more expensive. So, we need to restrict switches to certain locations from cost considerations and need to use hub at the other places. So, where to use which one? Now, a common sense is that we need to use a switch port for computers which are heavy generators and consumers of network traffic, and we know that servers account for much of the network traffic, and therefore, natural that we connect a server to a switch rather than a hub, because if it is connected to a hub, it will increase collision, it will cause collisions with other computers on the hub, and it will reduce the throughput. So, you might find that desktops and low end servers, etc., these are connected to a hub, and the hub in turn is networked through a switch, whereas a server which is heavily used is connected to a switch port, right. So, that the it does not participate in the LAN activities here, and collisions do not occur here, right. Is that okay? Now, let us proceed towards discussing Ethernet in real time communication. Can we use Ethernet in real time communication? What do you think? What can be the problem using Ethernet in a real time situation?
Ethernet, whenever a collision occurs, there is an alteration thing called back of algorithm.
Yes.
That will can lead to any amount of time. There is no perfect bound on that algorithm.
Okay. So, the Ethernet does not guarantee by which a transmission can complete, and theoretically the communication may never take place if it just keeps on experiencing collisions. But let us look at it in more closer. The main problem is that one of the main problem is that under high load situations, we have the delays and drops. The delays in the communication increases very rapidly. As the load increases, the delays would increase very rapidly, and also there will be a drop in throughput. If you look at it, as the load increases here, it increases slowly and then suddenly it becomes almost unusable. Latency increases very rapidly. So, typical performance of any Ethernet. You can even experiment by generating large traffic and larger traffic. See that there are some threshold values after which it becomes almost unusable. Why is this situation?
Because of more and more collisions.
Yeah, right. So, the main reason is that number of collisions increase rapidly as the load increases. So, if there is no collision, it just gets transmitted. Then if there is a collision, few nodes collide, there are a chance that as the load increases, they collide again and again, leads to futile transmissions. They just keep on transmitting, resulting in a collision, and if the load increases further, there may be zero throughput, just keep on colliding. And this is one of the main reason why the Ethernet networks cannot be used in a real time application, because consider the situation where there is a alarm avalanche or something, and then the load drastically increases and the throughput reduces, the delays increase. Okay. So, this is a common knowledge that we need to have before we discuss further. Now, let us see how hard real time communication can occur in a LAN. Many times there are constant bit rate traffic, but there can be other types of traffic, and another one thing that we need to understand is typically the network utilization is kept low. Only when there are alarm avalanche and sudden generation of traffic, the load increases, but typically they operate under low utilization and low load, and the predictability is more important than the utilization aspects. And since the load due to the hard real time messages is low, whenever these messages are not there, the soft and non real time traffic are allowed to be transmitted, only when the hard real time messages do not exist. We will examine three main categories of protocols. One goes by the name global priority protocols. Here all the messages are assigned priority, unique priority values, and based on the priority values they are assigned slots to transmit. A bounded access scheduling, where the priorities are not really with the messages, but with the stations they are given some time to transmit, and within that they can locally schedule the messages. And then we have the calendar based protocols, where they just reserve some time slots are reserved and then they transmit. Now, let us look at the global priority protocols. Here each message is assigned a priority value irrespective of the node at which the message arises. All are assigned priority values, and the MAC layer protocol tries to ensure that at any instant of time only the highest priority message is served. And once we can achieve this, that all the messages are assigned the priorities, and at any time only the highest priority message will be solved, we can think of using RMA or EDF to schedule messages. So, it basically boils down to something like a task scheduling. There also we had the concept of priorities to tasks, and then we found that RMA and EDF are the optimal algorithms to schedule the processor. We can think of the network here as processor, and the messages are assigned priorities which are analogous possibly to the tasks, and then we schedule them using RMA or EDF. unfortunately, there are many issues. We will just discuss couple of them, which make implementing RMA or EDF based solution rather inefficient. It is not really analogous to task scheduling on a processor. Let us see the complications. One is that we can stop a task when a higher priority task comes, we can preempt it and then we can restart it later. But what about packet? Either you transmit it fully or you do not. You can't just stop it halfway and then continue later. Does not work that way. Unlike tasks, packet transmissions cannot be meaningfully preempted. And also, here the stations, the nodes are distributed, and it is difficult to have a global knowledge of which node has the highest priority message at an instant. Cannot instantaneously determine the highest priority message because we do not have a global knowledge. They are distributed on different nodes network, and network transmission does take time. So, because of the delay, we do not have a global knowledge. Now, we will look at calendar based protocol, bounded access protocol, countdown protocol and virtual time protocol. So, let us look at that. The calendar based protocol used in very simple applications where there are just few sets of messages and few nodes. We will see or just observe that it does not work and tell me why it will not work when the load on the network, I mean there are many nodes and many types of messages to be transmitted. The calendar based protocol may not be a good solution. Let us look at that. Please observe that. Now, let us first see how the protocol works. As the name of the protocol suggests, there is a calendar which is maintained at every node. A copy of the calendar is present in every node, and the calendar indicates the time period during which a node is allowed to transmit. So, for every node there are slots which are assigned to them during which they will transmit. Copy of the calendar is maintained at every node and contains information about the access times reserved for guaranteed messages from all nodes. So, these are the hard real time messages. So, the times, transmission times are reserved for guaranteed messages. But it is possible that there are many other types of messages other than the hard real time messages which arise at specific nodes. When a message with no reserved slot arrives, then the node where the message arrives, it looks at its local calendar, finds a free slot and then broadcasts a control message for reserving that slot. It can't just start transmitting on a free slot because there might be other nodes which might try to transmit at the same time, right. So, it needs to reserve that slot, and once the control message is successful, then all nodes update their calendars accordingly and this transmits. But of course, it won't be a permanent slot, just transmit for that instant. So, we can think of it as a dynamic reservation technique. For some categories of messages there are static reservation, and for other messages there are dynamic reservation. Now, if the periodic messages are not predictable, depend on which node they will arise, etc., then it would become inefficient. But we know that hard real time messages, the mostly restricted, I mean the CBR kind of traffic, they are predictable from where they arise, etc. So, such messages it is efficient, because slots are reserved from the beginning by the designer, and they just keep transmitting, and other nodes do not use that slot. But for other categories of messages, aperiodic and sporadic messages, it becomes difficult, because each time reservation has to be done, and then it needs to transmit in a slot. So, lot of delay will be involved, and also if the periodic messages are not predictable, I mean they can arise anywhere, then it becomes difficult to handle those. Yes, please.
This calendar based protocol,
Yes.
you have said that it is static
Yes,
for some messages.
yes, right.
So, if it is static, even if one message under worst case
Yes.
misses its slot,
Yes.
then will it have effect on the remaining things, like this will get postponed?
Not really. See, the static reservation is made for CBR traffic, right. So, let us say every 100 millisecond need to transmit some packet of data. So, it will make a reservation for every 100 millisecond some slot of data, right, and those are predictable traffic. But if the traffic is unpredictable, then the reservation cannot be done. That is what I was just saying. Only for those which are predictable traffic, for that reservation is meaningful. For others, it is just temporarily they will try to book a free slot and transmit.
Even if it is predictable,
Yes.
it can so happen that a message is corrupted, or it has missed its slot deadline. In worst case, like
No, then it becomes complicated. Yeah, here it is assumed that a slot is assigned to it, it will transmit on that time.
so in case if it misses, then it becomes complicated.
Right, yeah. So, but what about the problems with this protocol? I mean, I said that it gets used for very simple applications. So, what do you think?
Only for periodic traffic.
Okay. Okay, so that we know that for periodic traffic can be used, and for others it becomes inefficient, lot of delays will be incurred. Yes.
We have to know which message is sent at what time. Everything should be predictable in the
Yeah,
real time.
yeah. So, very simple situations where the messages are almost totally predictable, it can be used in that situation.
So the network utilization may not be
Okay. No, see, if these are messages which are predictable, then appropriate reservations can be made and utilization can be high. For some applications, utilization can be high if the set of messages can be scheduled and we can find a schedule for that. So, reservation will be made based on that. So, let us look at the bounded access protocol. Here the access time of every node is bounded. So, they can transmit only for certain time, certain duration of time. So, this limits the time for which a node can transmit the packets, and since every node has a time for which it can transmit, the individual nodes can use a local algorithm to find out which are the higher priority messages at that local node, and during its slot it will transmit, right. So, each node in the network will be given some slot and they have to restrict themselves to using only that slot. That is the bounded access protocol. But the thing is that all nodes need not have the same slot, similar slot. The size of the slot need not be same for all the nodes in the network. it might vary depending on the kind of traffic they have, amount of data needs to be transmitted and so on. So, the individual nodes, once their slot comes, they determine the order in which the queued up packets are to be transmitted, and they use that to use their slot. So, we will look at this protocol, the bounded access protocol, in more detail. We will solve some problems and look at some examples and so on, because used in manufacturing situation quite frequently. We will also examine what is good about it and bad about it. Later we will do a performance comparison. We will see that where the bounded access protocols score over the other kinds of protocols. So, let us look at another protocol, the countdown protocol. We had seen this in some context in our previous discussions, in the context of controller area network that we discussed. So, that was actually a countdown protocol, even though we did not tell it that name that time. So, let us look at it. It is a global priority based protocol. That means that every message needs to have a priority value assigned to it. So, here the timeline is divided into fixed size intervals called as slots. So, if we let us say every 10 millisecond is a slot. At the start of each slot, an arbitration is carried out to determine the highest priority message at that instant. And after the arbitration period, so there are slots, and every slot to start with has an arbitration period, and at the end of the arbitration period it will be known which node has the highest priority message, and that node will be allowed to transmit. So, if we have fixed sized slots here, fixed size slots, the timeline is divided into fixed sized slots. Okay, it does not look like fixed size, but these are fixed sized slots, and each slot is preceded by an arbitration interval. It is exaggerated here. If the arbitration interval takes so much time, then it will be inefficient, right. The arbitration interval is much smaller, much smaller compared to the transmission interval. So, at the start of every slot, priority arbitration takes place, and once it is decided which node has the highest priority message at that instant, it utilizes the channel until the start of the next slot. And the duration for which the priority arbitration occurs is typically very small, denoted by delta. Choosing the size of this arbitration interval and the slot size is very important, and in each arbitration interval should be equal to the end-to-end propagation delay of the medium. The size of the arbitration interval should be equal to the end-to-end propagation delay of the medium. Why is that?
Otherwise, there can be collision.
No, not really. See, if it is less than that, what will happen?
Within that time, another slot may begin and another node may start sending message.
Not really. If it is less than that time, the propagation time, then there may be nodes trying to transmit where the collision will not be detected. So, the actual priority value will not, it will be possible to determine. So, the arbitration interval, so here actually the terminology is not correct, it is not slot delay, it is the arbitration interval should be at least equal to the end-to-end propagation delay of the medium. if the arbitration interval is smaller, then collisions won't be detected. So, initially the nodes keep on transmitting, and if there is a collision, then they know that there is a higher priority message which is getting transmitted, right. So, if the slot size is too large or the arbitration interval is too large, then there would be increased channel idle time. So, this is an example of the priority arbitration. So, to start with, every node starts transmitting their priority value. So, N1 transmits 0, assuming that higher priority is indicated by higher values of the priority. Sometimes we have the situation where the higher priority is indicated by lower priority value, but here it is the higher priority value. Just check here that N1, which has priority 10, is a lower priority compared to N2, which is priority 16, and N3 has priority 20. So, N1 at the start of the arbitration interval or at the start of the slot, the same thing, start of the slot is the start of the arbitration interval. They start transmitting from the MSB, and N1 transmits 0 and finds that 1 is being transmitted. So, it drops out, does not transmit its rest of the priority values. Then N2 finds that writes as 0, it could sense as 0, continues, and next transmits a 1 and senses as 0. So, it drops out. So, that is the way it works, and then N3 is the winner at the arbitration and it continues transmitting. So, if this becomes too small, then the protocol won't work, because nodes will falsely assume about their priorities. Let us look at the virtual time protocol, again a popular protocol. Here the state of the channel is sensed, and that is used to identify who can send a packet. So, again this is a global priority protocol. Each node is assigned a priority based on the highest priority message that it can transmit. But again, at a particular instant it may not have the highest priority message, right. So, it is the node responsible for a high priority message, does not mean that at every instant it has the highest priority message. So, that is a shortcoming of this protocol. Now, let us see the working. So, the node is assigned a priority based on the highest priority message it has, and here it should be, it waits for a period inversely proportional to the highest priority message that it has. So, what it really means is that depending on the priority, see they keep on sensing at periodic intervals, okay. And then a node, if it senses that the channel is idle, okay, it does not immediately start transmitting, but it waits for a time that is inversely proportional to its priority. So, the protocol would work as follows. Again the time has to be divided into slots, and at the start of the slot the arbitration would take place, where a node would start sensing here, okay, the channel, and it would also look at its own priority and wait for a period before which it can transmit the message. If it has the highest priority message, it will immediately start transmitting here. It won't wait much, but once the transmission occurs, then the lower priority, the node with the lower priority messages will start sensing slightly later. It will find that the channel is busy, and then it will not transmit, right. It knows that a higher priority message is already getting transmitted. So, the period for which a node waits before it tries to transmit is inversely proportional to the highest priority message that can be there at that node. So, each node with a packet to send waits for an interval of time which is inversely proportional to the priority of the highest priority message. The lower the priority of the message at a node, the longer it will wait. At every arbitration interval, it will keep on waiting until other higher priority messages have completed sensing, and it can be inferred that there is no higher priority messages for that interval, and then it can transmit. So, after waiting for certain time, it would sense the channel. If the channel is busy, it would wait again, and we know that the channel is busy. If a node finds that the channel is busy by the time it senses, what would it indicate? It would indicate that a higher priority transmission is taking place. So, if it finds it idle, knows that there are no higher priority messages, there can be lower priority messages, but no higher priority messages, and it would start to transmit. Now, let us look at the IEEE 802.5, which is a priority based token ring protocol. We had seen that token ring has some advantages over a bus protocol. So, here the header of the token contains two fields, a reservation field and a mode field. So, this was a protocol which was actually designed for a manufacturing automation situation. So, it was to start with designed for real time applications. So, there are the reservation and mode fields, and the token alternates between a reservation mode and a free mode. In the reservation mode, the different stations that are on the network, the different nodes, they reserve based on the priority of the message they have, they make a reservation. So, one bit will indicate the mode bit, whether it is a free mode or a reservation mode, and if it is in the reservation mode, then the different nodes on the network, as the token rotates, they would check the reservation field here, and then if they find that a lower value compared to their reservation, their message priority is there, then they would replace this with their own message priority and their own ID, right. Now, as this token reaches the sender, it would find that a reservation has been made by a node which has a higher priority message, and then it would put it in the free mode, and without any payload it will just send the token, and then the node which made the reservation will find that its own values are there, right, and then it will just capture the token. Is that okay? So, the way it works is that the stations make reservation in the reservation mode. When the mode bit in the reservation mode, they make a reservation. If they find that the reservation field has a lower priority, then the priority of the message that they have, then they write their own priority value here. But just writing the priority value here does not indicate that they will get the token next time, because another node might have a higher priority message which will replace it. So, as the token goes around and comes back to the sender, if it finds that the reservation field is changed, it has a higher priority than the priority of the message it has, then it will put in the free mode without any payload and transmit the token. But if finds that either nobody has made reservation or the priority value is less than the priority of the message that it itself has, then it will not change the mode to free mode. It will keep it in the reservation mode and continue to transmit. And of course, if it finds that there are no messages to send, it will just put it in the free mode and transmit. So, here we have assumed that again the messages are assigned priorities. It is a global priority protocol, and the priority value is stored in the reservation field. Different nodes examine the field, and if they have a higher priority, they store that in the field, and the messages are split into frames and attached are put in the payload with the token. As the token circulates, the reservation field is checked by each node, and if a node has a higher priority message, then it records its priority in the header in the appropriate field, the reservation field. It will write the priority value, and once the token is back to the sender, it checks the reservation status, and if there is a higher priority node which has registered its priority value in the reservation field, then it puts the token in the free mode and circulates. And after one complete circulation in the reservation mode, it is determined about if there is a higher priority message, and then it would be put in the free mode and it would start transmitting. Right? Is that looks okay? Now, we can make some observations based on which we will derive some results. One is that stated in the form of a theorem, the minimum time required to complete transmission of a frame is maximum of f and theta, where f is the frame transmission time. So, basically a token needs to be transmitted. So, this is the transmission time, and then theta is the propagation time. So, why do we say this? That the time required to complete transmission of a frame is maximum f comma theta, is that a node would not transmit the next frame until it has completed the last bit of the current frame being transmitted. So, that accounts for f. And also it should have received the header of the transmitted token back. If it has not received the header of the token back, then it would wait, because okay, let me just ask you, why should it wait?
Some other
Exactly. So, it won't know that if there is a higher priority message waiting to be transmitted, and then it should relinquish, isn't it? So, that is the reason why it should wait for the header to reach back. So, therefore, depending on what are the values of f, whether it is a very slow network where transmission takes more time, bandwidth is very low, which dominates the transmission propagation time, or whether the propagation time is large, it is a large network. Depending on that, the transmission time of a frame will depend, how frequently the frames keep on getting transmitted. Is that looks okay? Okay, we will derive some results based on these observations. Another observation which we will state in the form of theorem 2 is that if a node has a higher priority message which has arisen at a node, then it might undergo priority inversion for at most 2 into max f comma theta time units. So, the reason is that a higher priority message will undergo inversion until the reservation mode completes, and for the reservation mode to complete, it will take max f comma theta, and also the node receives the token in the free mode. So, the token needs to be transmitted, and in the worst case it can be just away from the node, and it will take max f comma theta. So, since both of these take max f comma theta, then the time for which a message can undergo inversion would be 2 into max f comma theta. So, these are two important results based on which we will derive some results just short while from now. We are just looking at the overview of the protocols, and we will see the working of 802.5 more detail. Another category of protocol is the window based protocol. Here again it is a global priority protocol, and again the time is divided into frames. Just observe that almost every protocol, global priority protocol that we discussed, the time is divided into frames, and at the start of the frame there is arbitration where it is decided which is currently the highest priority message, and then that is followed by transmission. So, here again the timeline is divided into frames, and there is a concept of a transmission window which is defined by some low and high priority messages. So, every node maintains these two values, the low value and the high value, every node. So, a node can transmit if it has a message whose priority lies within low and high priorities, but so can be with many other nodes. Many other nodes can find at the start of the FF frame that they have a message between the low and high priority value. So, this is the window that is defined here. The window that is defined here, so this is the priority values, some low value and a high value, and if a node finds that its priority falls within this window, it will start transmitting. But the only problem is that there can be several nodes which might find that they have a message whose priorities fits into the window, and then there will be a collision. So, there is the possibility of more than one node transmitting at the same time, which will lead to a collision, and on a collision each node increments the value of low, so that some of the nodes will get cut off, they will not transmit, but still there can be another collision, and then again the low value will keep on increasing until the highest the node with the highest message is found out. And on a free frame, if nobody is transmitting, then the low value will be decremented, because there are no higher priority messages. Maybe some lower priority messages might be waiting, do not know, and each time if there is a free frame, each node decrements the value of low. Of course, each low message will, transmission of a low message will be preceded by a free frame. right, but that is the inefficiency of the protocol. Now, we will look at some bounded access protocols, mainly 3 protocols we will look at. One is 802.4, IEEE 802.4. We had seen that 802.5 was a priority based protocol, and then the REther and the switched real time Ethernet. Let us look at the IEEE 802.4. Now, the way it works, let us try to understand the important points in its working. So, the protocol can work both in a token ring or a token bus network, and another name for this protocol is the timed token protocol. Here a node transmits only when it holds a token. And once it gets the token, it starts to transmit, but there is a bound for the time for which it can transmit. And this bound helps in providing real time guarantees, because in the worst case every node will hold for their own bounds, right. So, that will give us an indication of how long a message can have to wait in the worst case. One important parameter here is the target token rotation time, or TTRT. The TTRT is the expected time between 2 consecutive visits of a token to a node. So, when a token arrives at a node, it starts to transmit, and TTRT is the difference in time between 2 consecutive visits of a node. So, what does it indicate? It indicates how long or how much message might have to wait, and just see here that it is the expected time. TTRT is the expected time. So, what is the expected value for which a node would have to wait before it can start transmitting, or for how long the expected value of inversion, that a high priority or let us say a message that might need to get transmitted, right. Even if the message is there, it is high priority, it cannot be transmitted until it gets the token, and therefore, TTRT would be a expected value of that. But we know that for real time situations, expected value is not really a very useful thing, right. Now, let us see how we use this to get the worst case value. So, the TTRT is an important design parameter. It is initialized during the network setup, and the value of the TTRT is selected based on the messages that are there with the different nodes, the amount of data that needs to be transmitted, and so on. So, we will solve some problems based on this, depending on what is the size of the messages at different nodes and so on. And here the real time messages are considered to be periodic, and they are called as the synchronous messages. And the other types of messages, the non-real time, are called as asynchronous messages, and the asynchronous messages get transmitted only when there are no synchronous messages. Is that okay? So, the real time messages are called as synchronous messages, and only when there are no synchronous messages, the asynchronous messages will be transmitted. So, once a node gets hold of the token, it will first try to complete the synchronous messages, and then start transmitting the asynchronous messages until its time bound is over. And of course, if it does not have any real time messages at that instant, it would transmit asynchronous messages. When a node receives a token, transmits real time messages for a, if it finds that there are free time after transmitting the synchronous bandwidth. So, it starts transmitting the synchronous messages, and if it finds that there are some time left out after transmitting the synchronous traffic, then it starts transmitting the asynchronous messages. Of course, you might ask here that see, if it is a CBR kind of traffic, very predictable traffic, then how will the asynchronous, I mean why should it take less time? Because each time it should take the same amount of time to transmit, because similar traffic will be there with this. So, then where is the time to transmit the asynchronous messages? I mean, how will it transmit, complete its transmission early? So, would anybody like to answer how this can arise? Yes, anybody would like to answer anything? Okay. So, the answer is that even the the messages which are aperiodic, we need to consider them as synchronous. We need to reserve bandwidth them and consider synchronous messages if we need to transmit that with guarantee, right. So, that those messages which are aperiodic, they might occur or might not occur, and we will have a free slot. I mean, it will complete transmission earlier, it does not complete transmission early, depending on whether that specific message has arisen or has not arisen in that period.
Separate time has to be allotted for even asynchronous.
I mean, the ones that are important, the critical messages. For example, an alarm. For that, we have to have we have to consider that as a synchronous traffic. Otherwise, that node will not have any time left for it, right. So, once after completing transmission of the synchronous traffic, the node starts to transmit the asynchronous messages, and it can get the token early. See, even if there are only the synchronous traffic with it, right, if it has only CBR traffic, no asynchronous traffic, I am sorry, there are synchronous only CBR traffic and no aperiodic traffic which are of high priority, right. So, then how will it transmit the asynchronous messages? The idea is that sometimes it will receive the token early. It might so happen that its previous node neither had asynchronous nor synchronous traffic, because it had made reservation for some aperiodic traffic which did not arise. It neither had any asynchronous traffic to transmit, it just released the token early. So, in that case, the token can arise early at a node. So, we are running out of time now. We need some time to discuss this, about some results here, that for how long, I mean how do we distribute the time. The TTRT is the design parameter we had said, it is the expected time for a token to arrive at a node, and theta is the propagation time. So, how do we distribute this time of the token rotation among the different nodes in the network, and based on that we will do few problems on given a setup where we know that what are the nodes and what kind of traffic they have, what kind of messages they need to transmit, how do we assign slots to them. So, this we will discuss in the next lecture. So, we will stop here today.